entanglement. Now we're going to sort of extend the work to holography, and we're going to see this very nice new work from Lijie.
Yeah, thanks so much. This is a joint work with Umesh Vairani, who is also in the audience. So I guess everyone already knows that complexity theory have a lot to do with gravity, and if not, you should check the Lijie's talk and Jeff's talk. Yeah. So today's topic. So today we are going to consider, and they have talked about lots of connections between complexity theory and gravity. Today we are going to talk about another connection between gravity and computational complexity, which is what is the computational power of quantum gravity. I'll explain what I mean later in the talk. So, just to quickly refresh the background, I guess everyone already kind of knows. So ADS-CFT is a leading approach for quantum gravity and has been actively pursued for over the last 2 decades. And it shows a conjecture correspondence between this anti-de Sitter space, which is a quantum theory of gravity, through a dictionary to this conformal field theory, which is a quantum theory without gravity. And by having this bijection or dictionary or isomorphism, we can then construct a theory of quantum gravity simply by studying its non-gravity quantum theory, which is supposedly much simpler. So ADS-CFT, over the last decade, there are lots of connections between ADS-CFT and complexity theory. For example, I think so in the Monday's talk, you may already think like there's the wormhole growth paradox, which says that what is the dual of the volume of the black hole interior in the CFT theory. And you may already know that Susskind suggests that the dual here is actually quantum circuit complexity. So recall that ADS-CFT is like a two theory who are like isomorphic in the sense that everything in ADS should have a dual in CFT. And the volume of black hole is particularly interesting because it doesn't seem to correspond to anything in CFT before, but Susskind suggests that it's actually corresponds to quantum circuit complexity. And this, as you already know, this really started an epic journey on quantum complexity, gravity, and black hole. And there are lots of works following Susskind's beautiful proposal. But today I'm going to, here I just want to talk about one particular work by Bolan, Pfefferman, and Vairani. They show that they look at this equation through the lenses of complexity theory, because it's really something. It is really a beautiful proposal. So they observe that quantum circuit complexity, just like classical circuit complexity, is not something you can feel, because the existence of pseudo-random quantum states. So there are quantum states which look like completely hard random, and hard random states have maximum circuit complexity. So, but those pseudo-random states actually have very low complexity. So in the sense that you can have low complexity states who just look like completely maximally hard. They also show that this equation, they also show that this equation in some sense also imply the dictionary is exponentially hard in the presence of a black hole. So to translate from CFT to the ADS would require exponential time even for quantum computers. Finally, they also argue that this proposal is essentially the only way to resolve the paradox. So,
I have to protest that one. We understand that that's not actually the way that paradox is resolved. The conclusions of BFV are, of course, valid and correct, but it's resolved in a different way. It's not resolved using complexity equals volume.
Yeah.
It's a different dictionary entry that encodes the complexity of the dictionary when it's exponentially hard, which is, of course, consistent with BFV.
I see. Yeah, but is that like is that entry like looks similar as complexity in some sense? Like, is that feelable?
True, it's completely consistent with the conclusions of that 2019 paper, but Lenny's proposal is not the way that resolves the paradox.
Okay. Thanks for clarification.
It's the Python's lunch proposal, which is complexity is computed in a very different way, and it's again consistent with BFV.
I see. But that's still like a kind of complexity notion.
But that's a complexity of reconstruction, which is really what this should refer to, which is what BFV referred to.
Maybe we can talk later.
Maybe
you can talk later. I mean, maybe it's what kind of complexity it is, but.
Well, I think Lenny's proposal is just that the complexity equals volume is just wrong when you have when the dictionary is exponentially hard. And so I think in the example that you constructed, a dictionary is absolutely exponentially hard, and Lenny's proposal is just wrong. There is another way to, we can talk about it offline, yeah.
Okay, thanks so much for pointing it out. Yeah, so if you look at, now we know the dictionary is hard to compute. So actually, can we make use of them, the dictionary, computationally? Maybe you can use black hole as a computer, right? So here's BFV, they show that the dictionary is exponentially hard to compute, meaning that, or more precisely, they show that the black hole's exterior states, the complexity of that is exponentially hard to compute. But imagine you can jump in a black hole, then in some sense you can see the volume yourself, right? So that's a good thing to do, maybe. So the question is, can we solve hard problems in this way? Like, it seems like by jumping into a black hole, you kind of get additional computational power by seeing the volume, which is like correspond to complexity in some way. But the answer is probably no. There are lots of subtlety in this kind of thought experiment, and Scott Aronson has a wonderful blog on this. So I'm not going to spend too much time on it. But one problem is that if you think about it, what is the classical input of the hard problem you want to solve, right? So the black hole state is like a quantum state. And maybe you can think about it maybe as like, okay, how about I give you a description of a circuit generating the exterior quantum state of the black hole. I mean a quantum circuit. But then but then these questions get much more messy, and you can see how Scott argued that this actually does not provide you with additional power on his blog. So the question is really that, can we kind of use quantum gravity to solve a hard computational problem, and ideally not by jumping into a black hole? Okay. So to make progress, on this question, we are going to look at another principle. Another principle from holography, which is roughly, very loosely speaking, geometry corresponds to entanglement. So what do I mean? So why this is interesting? Because on one hand, geometry is something you can probably efficiently measure by observers in the ADS. And on the other hand, quantum entanglement is likely hard to compute by quantum computers. So therefore, this also seems something can give you additional computational power. By maybe you can make use of observer in ADS to actually measure the entanglement. So more precisely, there's this so-called Rui-Takayanagi formula says that in this ADS CFT correspondence, the area of certain minimum surface in ADS. So because this is 1D, area just means like a length equals the entanglement entropy between this part and the rest of the qubits. So CFT is just like a bunch of qubits lying on the boundary, and the ADS is the bulk in between. This also poses strong conditions on how entanglement entropy should look like in safety states. Because in safety states, the entropy is not arbitrary entropy. It has to look like as area of certain minimum surface, which is a very strong, constraint.
Can you be a little clearer on what you mean by efficiently measuring it in ADS? Like, I agree if I have access to the metric, it's just a trivial computation. But like in practice in the space-time, like I would have to start at a boundary and then like trace myself all the way along the geodesic, into the interior and out, which seems like a very hard, exhausting thing to do.
Yeah, I guess it really depends on how the dictionary works in some sense, and yeah, I guess like you can maybe one way to think about it is like, okay, I'm not a physicist, of course, but maybe you can think about how to can you measure the extent of gravity? Like you can like you don't have to like go all the way to.
Yeah, and I don't know if it's like algebraically, it's obviously in the center, like it's an observable, but it's the efficiently part, which is sort of I don't have a good sense of.
I see.
And
yeah.
especially since there's like this exponential redshift and blue shift as you go towards the center, like you might think that somehow it prevents you from doing something polynomially. I don't know if someone.
But if you're trying to simulate ADS CFT, wouldn't you have access to the measure, to the metric, and then maybe this?
Well, yeah, that's.
Yeah.
You got to be
I think it
careful
sort of
what you mean
depends how
by
you're
that, right?
how
I
you're
don't have
doing
the analytical form of the metric, right? Yeah, yes, I agree. Like as a super observer, I think it's very clear. It's the observers in ADS, which is like, I mean, when you guys wrote your paper on feelable volume, right, you had some notion of like families of observers following geodesics and like passing information out. I think you would probably need a similar thing to do.
Yeah, I'm not sure exactly if you should think about it that way, or as a sort of super observer, a simulator that has access to it. Anyway.
But what is the complexity parameter? Like, what if n is the number of particles
Or the entropy of a
in
black
the
hole.
CFT,
Yeah.
then wouldn't calculating volume the area also be polynomial in n?
Yeah.
In any case,
Yes.
Yeah, I guess I'm worried about time complexity, but
yeah, time-wise.
okay, right. It's a question of do you mean boundary time or bulk time? And so, yeah, it's maybe if you remove the word in ADS there, I would be perfectly happy.
Okay, yeah, I guess. I mean, yeah, let's maybe let's continue. We can like talk later. Yeah, I mean, of course, there are like implementation details how this thing can work.
I was just gonna briefly mention, like, I think in Jeff's talk yesterday, like, one of the things he said is, here the cylinder, he was like, there's actually some weird subtle things that happen with time where you can't actually go all the way in, but like the time is actually not infinite. So like the time, I mean, yeah, I think it comes down to like working out what the time actually is, and like, for instance, ADS CFT, and it actually doesn't come out to be like.
So it seems like
what you're saying,
right.
It should be probing from the boundary.
Netta, do you know if anyone has actually done this complicated? Like, it seems like it should be a pretty straightforward
I'm
gravity
actually confused about what is meant here, because if I have some entanglement wedge which goes into the black hole,
Yeah.
and imagine putting observers everywhere on the RT surface, and then wanting to aggregate their observations and so they can compute the area, they are not going to be able to meet before they reach a singularity. So I would not say that it can be efficiently measured.
Yeah, let's say that's no
right.
black hole for
Also,
now.
this is not a time like geodesic, it's a space
It's a
like
space like
geodesic,
geodesic,
so I
so
can't
there's no
really track
observer.
that.
Maybe also like a different philosophy, like I think a lot of the times it's helpful to think of this as just all being simulated on the quantum computer. So if you can simulate the whole system on a quantum computer, well, of course you can aggregate information from observers in the bulk who, like, if they were actually living in the space, would not be able to perform.
So I think for simulation, what we're talking about is how hard it is to simulate parts of the bulk in a quantum computer that we think of as living on the boundary. And in that case, I think it sometimes is the case that we can do this efficiently up to the minimal surface, but sometimes it's not, and it really depends on whether there are any holdups on the way there. If there are any other locally minimal but not globally minimal surfaces. And if there are, then it's not possible to do the efficient simulation. I don't know if it's getting too much in the weeds of it. Yeah.
You can keep going.
Yeah, thanks so much. Yeah. Okay, yeah. So that's another interesting motivation on its principle. So BFV talk about the hardness of this of computing this dictionary, And that's also another work by Ahrens and Pollack who shows that, so at least in like two-dimensional bulk, you can actually do the reconstruction. I mean, compute the dictionary in some sense from, you can reconstruct the geometry from all the entanglement entropy of all contiguous boundary regions of the CFT states. And you can do that in polynomial time. So if you look at this, this seems to contradict what BFV showed, because they show the dictionary is exponentially hard. So the answer to this question is that the entropy itself may actually be hard to compute given the CFT states. And indeed, as you have seen in the previous talk, this exactly motivates the definition. I mean, the hardness of computing entropy motivates the definition of pseudo-entangled quantum states. So here we have two ensembles of quantum states such that, so first, no polynomial time or subexponential time, depending on your assumptions. Quantum algorithms can distinguish them, even given polynomial number of copies, under standard crypto assumptions like one-way function exists. Second, these two ensembles of quantum states, they have vastly different quantum entanglement entropy. And depending on the construction, it may be across some partitions, bipartitions, or maybe across all bipartitions. And they construct pseudo-entangled quantum states, assuming the existence of quantum secure one-way function. So then this construction provides the precise sense that in what sense quantum entanglement entropy is hard to compute. Because if you can compute the quantum entanglement entropy, you can actually distinguish these two ensembles of quantum states. But also under one-way function exists, no one can distinguish them. So distinguishing them is as hard as breaking one-way functions. But still, the construction it's kind of not super physical, because they make use of some pseudo-random functions. So one question is, can we actually construct pseudo-entangled CFT states? That can make this notion works in holography. But of course, what do I mean by CFT states? So a cleaner question would just be that, can you construct pseudo-entangled states that satisfy the RT condition, in the sense that all the, for every boundary partition, the entropy just corresponds to the minimum surface of the geometry. So to study this question, we'll work in the tensor network toy model of ADS-CFT. So this is a toy model because it's only works in two-dimensional space. It's static, there's no time, and it also does not capture many features of ADS-CFT. It has been studied by many people in the last 2 decades, and you should check Tamara's talk yesterday, because they are on the most recent results. So a tensor network is just like a bunch of tensors contracted through wires. And the geometry of the ADS is simply the structure of the network. And CFT states just correspond to all the boundary legs. You can think about all those small circles that are qubit on each of the small circles. So here we only consider holographic states, meaning that or like equivalently, we are just fix the bulk state to be like a fixed product state, because we don't want to consider the bulk entanglement. So just to keep things simple. Okay, so this looks a little bit. This is nice, but can we like make it more friendly to CS people like me? So just to like make it even more CS friendly, we can think about the geometry of ADS simply as a planar graph with a boundary circle. So here you can see a very very small geometry. You have like a planar graph, and all those faces correspond to a discretized region. And so if you want to go from here to here, it just crosses two regions. And And for CFT, just think about it as a cycle of qubits living on the boundary. So there are 8 qubits. They can be like very entangled. And the information of the ADS planar graph is encoded in the CFT quantum state on the boundary via the RT formula. The RT formula for contiguous boundary regions is that the distance between, it says that the distance between the 2 endpoints of this boundary in ADS equals the entanglement entropy of this part A in the CFT.
What do the numbers in the regions mean? What do the integers in this region mean in the picture?
Oh, it just means the distance. So if you start here, then the distance 1, 2, 3, 2, 1. It just means the distance from this starting, from this point. Yeah. Because I'm just trying to, so it's like it's going to be the shortest path. And so for partition of the boundary to, even for general, for any boundary region A, the RT formula says something similar but a bit more general. It says the mean cut between A and the complement of A in ADS equals the entropy between A and the complement of A in CFT. So if you have if it's just one region, then it becomes the shortest path. But if you have many regions, it becomes the mean cut.
This is a theorem or this is a conjecture?
This is a conjecture, I think, in the actual ADS CFT.
Good to know. I mean, it's stated and coming from the outside.
In low dimensions, if you give me entropys on the boundary, I can produce a graph with these properties. That's what like Scott and I did, but we have no idea how to do it in high dimension.
Similar theorem actually. Yes.
Yeah.
So,
No, but so even for planar graphs, I know it's true on a line. That's all I know.
Yeah, so in some toy model, you can prove that.
It's a definition. It doesn't look like a definition.
I think that's the best way to describe it. It's either a conjecture or a theorem.
Yeah, okay. In some toy model, you can prove this.
No, but anyway, the two sides of the equation are defined separately, not one by the other. Yeah, but it's also different.
My sense would be that
Yeah, if you like, in the same sense that you could define holographic complexity to be volume, you could define holographic entropy to be this min-cut thing.
Yeah.
And then you can ask the question of when does this holographic entropy correspond to a real entropy, and when it does, you say the state is holographic. Like, I think that's the way physicists would do it. But yes, and in that case, it's a definition not of what the entropy is, but a definition of what states, holographic states are. They're things where there's a correspondence like this.
when I looked at this, I thought, okay, so my sense is that actually like the RT formula and the HRT formula is pretty well generally accepted in ADS-CFT. There's just like enough of it, like evidence and like kind of physics level rigor of proofs in some cases. But I would say like this is like it feels like this is like the analog of the RT formula you were saying, right? Like this is what the RT formula.
Yeah, it's like a toy model. Yeah, right.
Yeah. But sorry, so I actually have a question. So yeah, so my question actually was, what's the difference between the planar graphs you can consider and like the tensor network models? Because it seems like if you can consider any planar graph, like how much of a difference is there between the tensor network codes?
Tensor network is just like a concrete way of turning planar graph into a state, right? So just think about this as a structure of a tensor network. That's what we will do anyway. Yeah,
okay, so there's not that much difference between the planar graphs you can handle and the tensor networks.
Yeah.
Okay.
Yeah. And I'm just trying to keep things super simple. Okay, so any other questions about the formulation? Yeah. Okay. So maybe now let's get to our result. So we show that we can construct pseudo-entangled holographic tree states with exact RT formula. So what do I mean? So let T be an arbitrary tree such that all the non-boundary nodes have even degree. Then we can construct two ensembles of tensor networks such that their corresponding holographic states on their boundary are pseudo-entangled in the following sense. So first, they are computationally indistinguishable given polynomial number of samples under one function exists. And second, both of them satisfy exact RT formula with respect to this tree T as the min cut graph, and but with different weights.
So, what are the weights? What are the weights?
Oh, so for example, in this picture, the edge here can actually have weight. So like here it's like all they have unitary weight. So it's like 0, 1, 2. But this can be like 2. It's that would be like a 0, 2 or something.
So if you have different weights, it's a different metric, a different
geometry.
Okay, so they satisfy the formula, but on different sides.
Yeah,
RT formula.
And with different condition. Yeah. So
So what is pseudo-entangled about these things if they actually satisfy the argument?
Oh, I think I'm just trying to follow the naming convention, which means like you have two ensemble of states such that they look the same, but their entanglement are different. So here is exactly the situation. You have two ensemble of holographic states such that they look the same, but they satisfy the RT formula with respect to T with different weights, meaning that on some cut their entropy is different, right?
Okay, and it's different by a lot, because pseudo, I would say, it should be different by a lot.
Yeah, different by a lot. Like maybe a factor of 2, say.
Okay, but you're not comparing to the kind of by the book entanglement. It's just two families of both tensor network states, and the same. They just have different entanglement.
What do you mean?
Well, I mean, usually one compares to half-random states or something like that.
We have results like that, yeah. Okay.
But here you're assuming that all your states have well-defined semi-classical duals. Is that correct?
I think so,
That the
because
geometry makes sense in the dual state and the bulk. Is that reasonable, actually, for pseudo-entangled states, for these pseudo-entangled states, that they actually have a well-defined semi-classical?
I think that's a very nice question. I don't really know. It sounds maybe it's a good open question to think about.
But you sort of build this in here by having them live on tensor networks, right?
Yeah.
I think my interpretation is that you're constructing state. I mean, you'll show us all the results. My interpretation is you're constructing states that satisfy the analog of the RT formula, and that's just like a suggestion that maybe they do have some kind of, like maybe they are dual to some actual number.
I don't think he knows that they satisfy the RT formula. I think it's a conjecture that they satisfy the RT formula. Use the RT formula, as far as I understand, to compute the entropy, not the other. You don't check you don't have a separate way of checking that the area is equal to the entropy.
I mean, those states satisfy the RT formula, that can be proved. Right. It's not a conjecture. Of course, we need to assume one function exists to show that.
I think the RT formula only holds for states whose dual has a good semi-classical description, because our RT formula is derived using semi-classical physics.
I see. Yeah, I think then you can maybe think about it as some like a evidence that those states actually have semi-classical dual.
RT formula just means with respect to this graph, right?
Yeah,
There's no actual geometry or something, like there's no classical cavity behind it, right? It's just some
a graph. I guess you can turn a graph back into a metric.
It's known how to.
You can do that. I mean,
there's like I can construct like many different geometries that have a fixed amount.
There's no ABS.
Well, it's an ABS.
Okay. Yeah. Also, I guess I should mention like tree states are kind of popular in ADS-CFT, so it is actually kind of. I mean, I think that's a paper showing like you can actually distill a tree network from any actual CFT state.
May I just say to some people, just correct me if I'm wrong, but basically ADS-CFT is a conjecture about two models which are very complicated. One is logical field theory, CFT, and the other is ADS.
Yes.
And RD formula is proven only for semi-classical approximation of in the context of ADS CFT. That's one thing, if I understand correctly. And then there are toy models, which are not ADS CFT, but toy models of ADS CFT, not even special cases of ADS CFT, but toy models.
Yes.
And for those toy models to actually be helpful in order to study ADS CFT, we require, by definition, the RT formula. And that's what you're doing basically. You require and you build those examples, and then you prove that for those examples the RT formula is satisfied.
Yes.
And the rest is up to the physicists.
Okay. Yeah, I guess in order to do some like complexity theory argument, you have to do some discretization because the CFT has infinite dimensions. So yeah, okay. So this is one result. So another one is more general in the sense that we can actually strengthen that to an arbitrary planar graph satisfying some negative curvature condition from the happy code paper, which I'm not going to define here. So here we say that we can construct, given an arbitrary planar graph with some like a condition, we can construct two ensembles of tensor networks such that their corresponding holographic states are pseudo-entangled. They are indistinguishable, and they satisfy the RT formula approximately with respect to G. Again, here they satisfy the RT formula with respect to the same graph, but different weights. By approximately, I mean it's a multiplicative approximation with 1 plus minus epsilon. And the epsilon is something vanishing with number of qubits. So epsilon is indeed like a 1 over log of the dimension. So this is more general in the sense that it can work on arbitrary planar graph, but then we lose the exact RT formula in some sense. I guess one thing to say here is that in the literature, you can actually get exact RT formula if you allow the qubits dimension to be infinite or like exponential. But that's not very that will raise problem in complexity setting because you have to consider like hard random tensors of exponential size or something. That's not feasible. So we only want to consider like a polynomial local dimension. That's why you just get approximate RT formula. Yeah. That makes sense. So finally, that's another very interesting construction which we gave is that we can actually look at a random circuit, just like for example, a one-dimensional random quantum circuit, and view it as a tensor network. So imagine C sub D is a depth D random circuit on n d-dimensional qubits, and D is just polynomial. We can view by viewing it as a state, it actually corresponds to the canonical representation of this unitary as a state, which is simply the choice state. So the definition is here. So this is just another instance of a tensor network, but now all the bulk tensors are unitary, are hard random unitary. Then we can argue that under plausible assumptions, this boundary state, first, it looks like hard random when the depth is super constant. So we can think about it. So by looks like, I just mean pseudo-random state. I'll define that later. And also, we can prove that for any D, don't have to be like a super constant, this state satisfies the RT formula approximately in the same sense before, like 1 plus minus epsilon, when epsilon is like a 1 over log D. And the geometry, you can draw it. It's a graph like this. So the boundary states, there are some bulk nodes. And for example, if you consider the mean cut between this part, this is going to be like maybe 5 or 6. So as a corollary, if you think about these two states, like the depth, which is D, or 2D, clearly So they both look like high random states. So they also look like each other. That's one thing. And also because they satisfy the RT formula, so for T sub D, it satisfies this. It looks like it has entanglement entropy looks like this. And for T sub 2D, it looks like something much bigger. So on many cuts, they're going to be like they'll have very different mean cut and also very different entanglement. So these two will be like all pseudo-entangled states from its construction.
Sorry, when you say satisfies RT formula, do you mean across all of the cuts there?
Yes.
Okay, so was it so how this means that the choice state of a random circuit satisfies MMI? Was that known before?
Approximately, so maybe not exactly MMI. For MMI, you have some. I can say that it may satisfy MMI approximately.
Yeah. Okay. That's very not. Do you have any intuition why that should be true?
Well, it's just
What's MMI?
Patrick can explain if he wants, but yeah, it is.
Well, if it's basically a random tensor network state, then it should.
But I thought that was only in large qubit dimension.
There is a large.
Oh, okay. Sorry, maybe I just missed that.
Yeah,
Okay.
polynomial. Yeah.
Okay.
Yeah, that polynomial is crucial because I don't think it holds if you have like.
Okay. So this is you're mapping the random circuit to a random tensor network, and then it's just true because it holds for random tensor networks.
Random tensor networks, you have high random tensors, which is different from high random unitaries. But yes, morally they are pretty much the same. Actually, I think the same holds if you just forget about unitary and just put high random tensor here. It's just that then you need to make some less standard assumptions because I mean here random circuits we believe they they are sort of random and you can make nice assumption about them. But for high random tensors, things are less clear. But I think the everything here also works if you just replace those nodes by high random tensors.
Sorry, I'm confused about something basic. Whenever we're talking about an actual holographic theory, any cut that we make for the CFT, I mean, it's going to be extremely highly entangled with the rest of the system. And so I'm just not clear what you mean when you say that they're pseudo-entangled, in the sense that they're all going to be entangled at A over 4G.
Oh.
So it's not like it's not like this, it seems like you don't have an order of separation.
So okay, this definition just means that these two states, they are indistinguishable, but on some cuts, the entropy are very different. So for example,
Sorry, go ahead.
Sorry. So for example, for this cut, let's say this cut is simply the depth d. So in one case it's d, in another case it's 2d.
But sort of in terms of holographic parameters, what is the order parameter that that I have in the CFT that tells me that it's where one state is much more entangled than the other?
It's not. This is not the definition of pseudo-entangled states. This is here. We just mean that these two states have they look the same, but they have very different entanglement on some cuts.
I'm just trying to understand what you mean by quantitatively by very different entanglement.
It's just so what do you mean by holographic parameters?
Like the central charge of the CFT.
I think that's for you to figure out. The point of this talk is not to figure that out; it's to get you to figure it out.
Like, how large is the gap? Like, how large is the gap in the entanglement?
D versus 2D. I mean, you can change this to anything.
Okay. And D is the depth?
D is the depth, yeah. Yeah. So what do we?
Since we're talking about basic questions, maybe about this earlier, but I'm a little confused about the motivation where you say by measuring the surface in the bulk, we could solve a hard problem. The area of the surface, we could solve a hard problem. I'm trying to understand how that is different from a situation where I have a condensed matter system for which I know that in the ground state there's an area law, and I can just look at the object and measure the area of some surface with a ruler. And the reason I'm asking this is that you might object, well, you're using the fact that you know the state, and you've already done some theory that tells you that there's an area law in such a state. But the same thing is, I think, actually true in holography. When we say that the dictionary is such that we can talk about certain code subspaces, and in those code subspaces you have a smooth geometry of that area. But for example, I could take that entangled state that we started with and project, on a pure state in a subregion of the CFT. And if it's a typical pure state, it won't do very much to the bulk geometry, but it will replace the RT surface with kind of the end of the world. It still has the same area though. So it seems to me that this is using in some ways some knowledge about the state and some sort of theory that we get from gravitational patterning rule about, that tells us it tells us an analog of the area law for condensed matter systems.
Maybe can I say something about that, Raphael? So if you could do that with a condensed matter system by measuring something with a ruler that allowed you to break the one-way function, then you would be doing computation that went beyond quantum computers. So you would now have a super quantum computer on your hands in that condensed matter system.
But I'm not really checking the entanglement, right? What I'm really doing is I'm using a theory that predicted an area law for the entanglement, and now all I need to do is measure areas.
No, so think of it this way. You could say, well, when you implement Shor's algorithm on a quantum computer, you'd say, well, all I'm doing is using a theory. I mean, there was some theory that went into saying that if you compute this way, your output would be the factors. Now we're saying there's some theory, okay, that's fine, but eventually, if you can distinguish this kind of entanglement by using your ruler with the condensed matter system, you are actually solving a hard problem, no matter how you did it, no matter based on what theory. There's an input to this problem. It's a classical input. And you're trying to figure out some property of it. If you did it physically by some means, that would be an interesting consequence.
The difference to the example with the condensed matter system. I mean, I can also take a crystal and not put it in the ground state and engineer some extremely complicated entanglement, and it just won't look like a crystal anymore. It'll be vaporized, or it'll be some other complicated system. But if I see that it's a crystal at 0 temperature, I can use that in the theory of the crystal and of its ground state as input, and then say, okay, now I know what
You're making an assumption that it's exactly in the ground state, and don't these systems have lots of minima that are very close to the ground state?
Well, the analogy is not perfect, but in ADS, what I said, I think it's true.
Maybe we can keep going. And
Yeah.
We'll come back to that. I have a very simple question for Lijie. Much more simple. Is it important that these 2-qubit gates are random, or do you think there's some?
So for the RT formula, you only need them to be 2D line.
Oh, I see. So they could be like a Clifford. Circuit.
Yes, but I guess for Clifford, then you don't get entanglement because
you can learn.
Because you can learn the circuit. So that only. So, I see. So only assumption design for.
So I guess as long for most 2D design, you should be hard to, because for you have measure over 2D design, and most of the 2D design wouldn't have this nice property of Clifford.
It depends on what assumptions you're writing under the word plausible.
Oh, will we see that actually? Okay, so maybe let me say no. So the assumption is very simple. It's just saying that this circuit is a non-adaptive PRU. Yeah. So, but actually, we can kind of, for this one, right? So you actually show this is a very good design, it's like an omega log n design, or it's you can argue this is like a d times log n design in some sense.
Sure, that's quite different than being pseudo-random, right?
Yeah, sure.
I think under non-adaptivity, it's probably true. I don't think anyone has proven it, but random circuits are probably at least sort of non-adaptive pseudo-random states. Pseudo-random. You're saying if you have a non-adaptive PRU, you just get a pseudo-random state that's constructed.
Yeah.
So.
Can I say one thing? I would like to make my democratic vote that you just defer all questions that you want to, so that you can get through the rest of the time.
Yes, I agree.
But looking at the time, I probably have. Okay. Okay, actually, now if I feel like we'll have more questions. But anyway, so let's imagine we have a thought experiment. Suppose, okay, it's a very provocative thought experiment. Suppose you can somehow, let's imagine we treat this toy model very, very seriously, and we can prepare the CFT states, and somehow we can actually measure the geometry in the bulk by whatever some means. Then you can actually distinguish the pair of the pseudo-entangled CFT states, which we just constructed, because the geometry will actually tell you apart the CFT states. Although in the CFT side, they are just completely indistinguishable. So does this imply that quantum gravity can allow you to break one-way functions? Because the hardness of the breaking some of the pseudo-entangled CFT states are based on the existence of one-way functions. So
you can distinguish by calculating the area. Why does it immediately follow that if you have access to the geometry in the bulk, you're saying you can do that by calculating the area?
Not
right?
calculating, maybe like
Estimating the area.
if it's in the real world, you can try to measure it by yourself.
By measuring the area, and the discussion earlier was that this is not clear that you can do that.
Yeah, that, of course. So that's what I'm asking. Can you do that? Yeah. I guess that's a very that's actually the key question here. Can you do that? Yeah. And of course, it's just in a toy model, and there are all, and people have pointed out it may not be feasible, and also there are many other conditions from ADS-CFT which all construction are missing because it's just a toy model of tensor networks. Yeah. And a very interesting question is that all holographic states are kind of static. So if we want to prepare CFT states, in some sense, we need to have a dynamics of toy models of ADS-CFT such that you can actually prepare CFT states from maybe from R0 to from some like starting point to like the state you want. So can we justify? How do you prepare the CFT states as using some dynamics, maybe some strengthening of the toy model? And finally, more broadly, what is the model of computation for quantum gravity? Like, can we, based on those tensor network constructions, can we actually at least build a toy model of computation for quantum gravity? Yeah. I guess all questions are asked. So now so okay, let's see a little bit of the proofs. So we'll just try to look at this clean question. We want pseudo-entangled states that satisfy the RT conditions. So we actually give two ways. What is the question? Oh, so the question is,
Do there exists?
Can you construct? Oh, can you construct? Can you guess? Yeah. Can you construct pseudo-entangled states that satisfy the RT conditions? No, it's not a theory. Yeah. So we have to give two ways of doing so based on two key ideas. So two completely different ways of doing so. The one is just try to use the pseudo-randomness of random quantum circuits. Another one is use something called pseudo-entangled link states to modify the tensor network in some way. Which one do you want to see, actually? Maybe I can only finish one. Okay, there's no preference. I'll probably just go with my slide. Yeah. So first up, so we'll need to use something called perfect tensor. So a tensor is a perfect tensor if the number of legs is even, and also it's a unitary if you assign any half of the legs as inputs and the rest as outputs. So you can So they are very interesting because you can view them as a unitary in many, many different ways, as long as the number of inputs and outputs are the same. So what we're going to do is that first we'll consider an arbitrary tree tensor networks consisting of perfect tensors. And then we can prove that if given an arbitrary tree tensor networks with perfect tensors, we can show the boundary state satisfy the RT formula perfectly. And moreover, we can also show that they satisfy the RT formula even if one edge is replaced by a link state. And I think it just means that now we have like a small tensor here. It has 2 legs, and it works just as so if actually if the link state is just like EP appear, then it's just normal link. Yeah. And moreover, first, the RT formula still holds if you replace an edge with a link state. And second, the boundary state can be efficiently computed given the link state. That's what we can show. So then what's the construction? The construction, so using the result, building on the previous result by Aarons and al., we can actually show if that's a one-way function, then you can construct a pair of computationally indistinguishable link states, delta and pi, such that a link state is like a two qubit states, right? So that their entropy are very different, but they are computationally indistinguishable.
That means by measuring the quantum state at a long
So a link state is just like two qubits.
The link state itself is indistinguishable, or the
Yes.
link state you construct?
I mean, for this lemma, these two are indistinguishable. But then we'll show the boundary. So okay, as you have already said, the also entangled states would be tensor works with this link as delta, and versus tensor works with its link as pi.
Again, a quick question. So for this to be true, this local dimension D of the link state has to be super polynomial.
Yes.
Otherwise, you can do tomography on it.
Yes. It has to be superpolynomial. Yes.
And these are again ensembles of space.
Yes, they are ensemble of space. Yes. Otherwise, you cannot have like a pseudo-entanglement. Yeah. So that's our construction. Okay, so how do we show the RT formula? That's the math part. So the idea is that imagine you have tensor networks, and say we want to show it satisfies the RT formula satisfied with this particular partition on the boundary. What you do is that so first we look at the min cut between this part and this part. So the min cut here is just going to be these two edges. Then we kind of think about the min cut as just some pairs of EPR states. Because like a normal link can be you can think about them as EPRs. Then the goal is to orient edges so that the whole network can be interpreted as two efficient isometry, P and Q. So you can do the orientation because they are perfect tensors. You can interpret them as unitary any way you want, as long as the number of inputs and outputs are the same. So what you want to do is you want to interpret this part as an isometry from the bottom half of the EPRs to the A, and this part as an isometry from the upper half of the EPRs to the complement of A. And if you can do this, then just by definition of entanglement, you can write, because T can be written as something like this. Then this part is on A, this part is on complement of A. Therefore, the entropy between A and the complement is just gamma times log D. So this is how you establish. So how you wish to establish RT formula by.
Why is it important that it's efficient? I mean, you're just doing a mathematical plane, right? The entropy is something. Why do you care about the efficiency of the isometry?
Because I think it's because you would actually want to get this T, and to get this T, you actually want to prepare this T, because like you want to argue that your states are constructible in polynomial time. So if this, but not for this proof. Yeah, but if P and Q are efficient, then you can actually compute T this way, right?
I'm a little confused about another thing, which is, so the bond dimension here has to be super polynomial, right?
Yeah.
So that means the tensors are super polynomial size objects. So why does the state even have a polynomial silence.
Oh, here you can actually use random Clifford tensors. That's fine.
Oh, I see. Okay.
Let me see if I can yeah, maybe let's skip this proof and just look at the random circuit stuff. So to construct the isometry, what you do, you can actually apply max flow min cut theorem. You can find some min cut, some max flow between A and the complement of A, and then you try to route the edges in some like very cool way. You can then interpret the whole thing as some isometries, and this even works with pseudo-entanglement states in place of a normal edge. Like that's some case analysis. It's interesting, but it's not a. But given the interest of time, let's just quickly skip this. Okay. So now let's look at the second. Okay, I have 3 minutes. So now let's look at the second construction. So recall that we are just interpreting a random circuit as tensor networks, and then we have this choice state as on their boundary. So the conjecture, the preset conjecture is that when the depth is super constant, this random circuit is a non-adaptive PRU. And this conjecture would imply this T sub D is a PRS. Oh, so PRS just means pseudo-random states, which is something like an ensemble of pure states is a PRS, if that for every polynomial M and every polynomial time quantum algorithm, A cannot distinguish M copies of phi with M copies of a single high random state. And that's PRS. For PRU, it's very similar. It's that you have a unitary, you have an ensemble of unitary as oracle now, and you can make polynomial number queries to that in a non-adaptive way. And you want to say that the first case that you get this ensemble of unitary, the second case that you get a high random unitary, and these two cases cannot be distinguished by any polynomial time algorithm. So that's non-adaptive PRU. Yeah, I think yes.
Yes.
Yeah, constant depths they are not. You can learn something non-trivial about them. I think.
They don't generate enough entanglement. Is that the idea?
Yes. You can.
Swap test with distinguish.
Yeah, that probably just like MPS with polynomial bound dimension. Yeah.
All of this, in constant depth, they are not PRU.
I'm not sure, but I mean, a quick proof would be you apply this to all 0. Then you have a state which should be a high random state. But then you just like quickly try to test the entanglement. You can actually find out that the entanglement is not as good as a high random state because you only have.
I was just going to say there's some results on learning constant depth circuits that you could talk to Robert about.
Yeah, sure, but you don't have to learn it to.
That's true.
Yeah. Because maybe that is too strong, and you don't necessarily believe it. But we can also show like this state family is an approximate two-state design. So at least, and also plausibly they are probably D design or even D times log n design. By assuming some conjectures from a paper by Hunter Jones. This is kind of just using some statistic mechanics model to calculate the frame potential of random circuits, and you can actually show that. So the corollary here is that these two ensemble of states look very similar. I mean, they're indistinguishable. And so I also want to say a little bit on like, so this actually gives you a very nice toy model of CFT evolution, because you can just keep popping up those tensors. Okay, this is not this is just a toy model of evolution in some sense. Like the networks evolves by having bulk tensors popping up one by one, and all the intermediate tensor networks, for example, this one you get during the evolution is still define holographic state satisfying the RT formula. And as depth goes up, the holographic states eventually become pseudo-random. Perhaps this is a toy model of some expanding space. You can also, if you want, you can also wrap things up as a cylinder. That may look even better. Yeah. So finally, I want to, so not all unitary tensor networks can. So most of the unitary tensor networks, they cannot be interpreted as deep learning circuits. Deep learning circuits are just like very special type of networks. So can we say something more general? So for example, look at this very cute diamond network. It's probably not pseudo-random because there are not enough, if you look at the leftmost and the rightmost, there are not enough scrambling going on. So it's definitely not a pseudo-random unitary. But still the intuition is that if I only play a little bit deep in the bulk, let's say I just try to modify those two gates like this, then there still should be enough scrambling or like mixing to hide the difference of the geometry deep in the bulk on the boundary. So we conjecture that for two random networks that only differ very deep in the bulk, their corresponding boundary states should look like the same, meaning that the polynomial number of samples, you should not be able to tell them apart in polynomial time. We can prove that through some brute force calculation, the boundary states are statistically close given two copies. This is again proven by doing some like lattice, some lattice magnet models of calculation of those random circuits. So finally, I believe all results still hold if high random unitaries are replaced by high random tensors, which is exactly the model introduced by Hayden et al. The challenge or the subtlety here is that because we need to argue about the pseudo-randomness, and the high random tensors are slightly different from high random circuits, we have to make some ad hoc hardness assumptions instead of more plausible one about random circuits. But I think those things make perfect sense. It's just that also in terms of calculation, high random tensors, there's like you have to do the renormalization because you have to divide it by the norm, which is also give you some technical details in doing the calculation. Okay, so finally, let's quickly look at the open problems. So those toy models, what do they say about the computational power of quantum gravity? Can we use them to build a model for gravity computer, for example? And can we have more plausible time evolution models for CFT states? And how about the robustness to errors? Can we put a fault tolerance threshold theorem for a quantum gravity computer, maybe? So finally, besides complexity equals volume and the geometry equals entanglement, there are other interesting ideas from quantum gravity can have intriguing consequence for computation. For example, I just learned there are some post-selection going on in some models of quantum gravity. So maybe that can be useful. I mean, just as a food for thought. Yeah. That's all.
One or two questions?
I really want to express this one more time. I think this doesn't work in either direction. So for example, by measuring the area of some surface, even in a nice smooth geometry, before we worry about spoiling the true entanglement, you do not learn anything about the entanglement entropy of the boundary state. For example, I can measure the area of a black hole horizon. And that area could represent the entanglement entropy of the boundary, and it could also not represent it if behind the horizon the geometry closes off smoothly. It depends on the state. You have to know the state to start with. And conversely, if you start with a much more complicated state, you don't know if there's going to be a bulk dual at all. And until you know what the bulk dual is, you have no idea where to go and which areas to measure that have anything to do with the entanglement entropy of that boundary state. So I just don't see a scenario under which you could possibly break any protection coming from the difficulty of problem. I don't see it.
Just on the discussion front, we are going to have a panel at 3:30. We're going to try to hash some of these things out, so I encourage you to come.
Yeah, we have a faculty meeting sadly.
Oh, that makes clear which you should choose.
One
more question.
Yeah, so actually following up on this question, Lijie, thanks for the nice talk. And I was curious whether like a model like this could be interpreted as evidence for arguing, for example, whether given a state of the CFT, whether it's computationally hard to determine whether you're in the code space or not. So in the code space of the duality. So given a state, determining whether it has a geometric dual or not. Maybe this question doesn't make sense. I apologize.
You formalize the condition exactly.
I think by the definition of a code space, which is, you start with a state and you only have simply constructed states near it that you consider in the code subspace. You can always do that once you pick.
No, but I mean, if I give you some states, like many copies of the states, and I want to know, is it in the code space, in a code space or not, or is it some crazy state that I should not be able to represent in this?
Right. So you project it onto the code subspace many times and see if the overlaps are high. Right.
Yeah, that's computation. Maybe that's computation hard to do.
I think the issue in holography is that there's many possible code subspaces or more so. Like there's supposed to be roughly like one for every distinct semi-classical geometry. And so I think it's very easy to tell whether it is in the code, a particular code subspace, but telling whether it's in any could be very difficult.
Okay, in the interest of time, I'm going to cut off this discussion. We'll take it offline. Let's thank Lijie again.